Hello everyone and welcome back again. Today we'll look at an sinusoidal steady state analysis. So this topic combines what we've already learned, which are Dondo analysis, mesh analysis, superposition, source transformation, Thevenin and Northern theorems, combined with what we've learned in this semester, which are time domain and frequency domain and stuff like that. So let's take a look at our example. So we have a normal circuit here with resistors, sources, capacitors, and that stuff. Suppose that we want to find Ix over here. How do we do that in this using the analysis that I've just mentioned? So firstly, it is important to first identify what is being given to us. So what information can be obtained? So over here we see two sources, but these two sources are in time domain form. If we want to use them, it is convenient to convert them into frequency domain or phasor form first. So the first given is, of course, very easy. The angular frequency over here, as you can see, 6 radian per second, and then we have the current source and the voltage source, but we want to convert them into frequency domain form. So using, just substitute in a number over here and just ignore this 6t's. Now we have more given to us. If you took a look at these two resistor and three resistor, three resistor and the two capacitors and one inductor. But as you can see, we need to convert them first into ohm. So the first one, we use the following formula: 1 over J angular frequency time that the capacitance that is given here. So it is in, of course, in imaginary form. Next one, inductor. To convert, we just substitute again J times angular frequency and then the inductor sense rate. And this one is optional, you can do it later, but for me I just do it here so that it will be easy for solving later problems. So yeah, it's capacitor the same. Now when we look at this circuit, if we use mesh or nodal analysis, it will be very difficult. For example, like mesh, we have 3 meshes here and you have a lot of equations, so we can use, it is much preferably if you use Thevenin or Northern theorem. It will make life much easier for us to solve this Ix. So we are applying Northern theorem here. The Ix is over here, so we can just say cut this part out, just disregard this part for the moment. We'll come back later. So the circuit becomes like this. As you can see, terminal 21. So first thing first, it is up to you to analyze whether whichever you like, Rn or In first. I think it's not really that much of a difference in terms of difficulty, but I will go with Rn first. Okay, so let's first analyze Rn first. So as we can see here, the sources are neglected. So the voltage source and the current source that were used to be here, so we don't consider them for the moment. And as you can see, this capacitor, this resistor, and this inductor are in the same node, so we can say that they are in series. So normal normal stuff over here, just add them all up, and then all of these will be in parallel with this 2 ohm resistor. So again, apply the formula. Once that, you will get this number, which is, in this case we call them Zn. We've done with our first part. Now let's proceed with Ln. Again, same circuit, terminal 21 here, but if you look carefully, you can see that in this, we know certainly that In is here, so we can say that there's no current flowing through this 2 ohm resistor over here. We can just completely ignore this. So what do we use to get In over here? Well, I'm suggesting mesh analysis, because as you can see here, we have 2 meshes, and the first mesh is already easy, so it is best suited here. First one, I1, I2. You can convert this into imaginary form by use. It will be much easier for you to calculate the final number. So you just use r cos theta and r sin theta. You get these numbers. So firstly, we know that I1 will be equal to the current over here, because they are going in the same direction. So now what do we do for I2? Well, we apply KVL to the second mesh, and as you can see, if you've done your math correctly, you will get this number for I2. But we also see that I2 is equal to In, so we now get our In. Now that we've completed our second part, let's move to the final part in constructing the northern equivalent circuit. So usually we have a current source over here, and then as many as Zn as you like. So this is our In from the third part, and this is our Zn, and this part, recall that there was a 0.5 farad capacitor here and a 1 ohm resistor here. We can just combine them so that we can get the Z in this part. Now that we got that, we can easily calculate for Ix, which you can use standard current division over here. Just plug in the formula, use the current, use the Saturn over here. We get this number, which use the formula again, 10 7 1 minus y over x, and then you get this degree, and of course this one just square root of the two numbers to the power 2, right? But this is in time excuse me, but this is in frequency domain form. We want the final answer to be in time domain form, so just plug in the number over here, and then we use the same angular frequency, and that will be our final answer.